Section 815 is called phase sequence. And some of you may already know this, but say I take a three-phase motor and I wire it as phase A, B, and C. If I do that, the motor will turn, say, clockwise. Now, if I were to swap any of those two phases and say instead of going ABC, I put BAC or CBA, swapping any two phases will cause the motor to turn in the opposite direction. So that motor that was turning clockwise would now turn counterclockwise, because what we end up doing is we change the sequence of the peaks of those three sine waves, and we therefore change the magnetic field that's occurring internally in the motor, and it actually turns the opposite way. And we'll go into some more detail with that later. But that's important. And a lot of times, say you have a pump, right? And you want that motor to power the pump, you want to make sure it's turning the right way. Because if you don't, that pump might suddenly become a vacuum, right? And that could cause some real problems for the situation. And there are instruments out there, we have them in the lab too, that show us how to determine the phase sequence before we actually start the motor or connect it to a load. So let's look at that. So in section 815, he begins, he says, in addition to line voltage and frequency, the three-phase system has an important property called phase sequence, okay? So we want to be familiar with that, phase sequence. It's an important thing for us to be able to deal with. And so maybe we should write it first, right? Phase sequence. And it references in terms of how we would see the various phases as in the rotation of say a three-phase motor. Okay, so consequently, in three-phase systems, phase sequence is as important as the frequency and the voltage are, because we have to know which way the motor is going to turn, right? That's important. A load is designed to, and a system is designed to turn in a certain direction. The phase sequence means the order in which the three-line voltages become successively positive, right? When we're talking in terms of our sine waves, and there are three of them, which as they rotate through, which one, what is the phase sequence? Is it as they become positive, A, B, and C? Or could it be B, A, and C? Or could it be C, B, and A? There's different possibilities there. And so he goes through with this analogy here in this figure 823, and he says sort of an intuitive understanding of what's going on is I'm looking at this is me, and there's my eye, and I would usually have reading glasses on. And as I look at this, what I'm seeing as this rotates counterclockwise, I'm seeing a sequence of A, B, C. Okay, and so that would repeat itself, ABC, ABC, and we'll call that maybe a positive sequence. We'll call that a positive sequence. It could be described as ABC, BCA, or CAB, right? Any of those would describe the same thing. If the same disk turns clockwise, we would call the sequence differently, right? It would be, if it turned clockwise here, all of a sudden, it would be it would be A, C, B, okay? And that could be described as ACB or CBA or BAC, depending on where you are in the sequence. So clearly there's a difference between what we'd call a positive sequence and what we'll call this as a negative sequence. So if you interchange any two letters on the disk that we're looking at, okay, Now he's drawn these for us here. I didn't have to, you know, go through all that. But if we change any two of the letters on the disk, you know, like he went from here, we will change the direction of the rotation. All right, so swapping any two phases changes the direction. And he shows us that with 825. If the letters A and C are interchanged, the result is shown in figure 825, and the sequence now becomes CBA, CBA, and that's shown as the same as the negative sequence generated by the disk in 824. Okay, so anyway, he says we conclude that for a given direction of rotation, a positive sequence can be converted to a negative sequence simply by interchanging two letters. Similarly, a negative sequence can be changed to a positive sequence by interchanging two letters. So if we can look at a system, like a three-phase system here, and this is figure 826, and we have terminals A, B, and C, and they're correctly represented by the revolving phasors shown in 826 B, okay, EAB, right here, EAB, this, all 120 degrees apart, right, as we look at that. Okay, so suppose the line voltages EAB, EBC, and ECA are correctly represented by the revolving phasors shown in 826B here. As they sweep past the horizontal axis in the conventional counterclockwise direction, they follow a EAB, EBC, ECA, and then all that just repeats. If we direct our attention to the first letter in each subscript, we will find that then it said, you look at the first letter and find the sequence ABC, ABC. The source shown in figure 826A is said to possess an ABC sequence. We can therefore state the following rule. When using the double subscript notation, the sequence of the first subscripts correspond to the phase sequence of the source. Okay, so EAB, EBC, and ECA, the first letters describe the sequence that we're talking about. Okay, let's see, he's got a little example, figure 817. 817, let's see if I can find that for us right quick, and we'll wrap this up. 817, the phase sequence of the source is known to be ACB. Draw the phasor diagram for that. And I think he's showing us that in figure 827 here. Okay, so you can follow that along and see what that looks like. It follows a sequence of A, C. Okay, so remember this is going counterclockwise. That's the norm. So this would be the first letters A, C, B. All right, we could reverse it. By, changing any of the two conductors. All this may appear to be a trivial change. It can be a major problem when large bus bars or high voltage transmission lines have to be interchanged. In practice, measures are taken so that the drastic mechanical changes do not have to be made at the last minute. The phase sequence of all major distribution systems is known in advance, and future connections are planned accordingly. Now, when we get into power systems, we talk about that in synchronizing large generators and how you have to know the phase sequence, because you can actually set up potential differences inside the machine. Potential differences can cause, severe damage to these things. And again, as you go through the rest of this, there's devices. We used to make them. Now they have specific digital devices that can tell you the phase sequence, so you know it in advance. And then the rest of the chapter tells you how to make power measurements, how the connections are made. Section 821 is really interesting, where you a remarkable single phase to a three-phase transformation you can do. But at some point, I guess we'll wrap this up and say, that's all we're going to really require in this. And our quizzes and homework will be based on the material that we've covered up through 815.